One of the benefits of JuMP, Julia's DSL and package for modeling optimization problems, is that it provides an abstraction layer over solvers. It allows you to replace one solver for another for the same problem with the same code. But why would you do that? One consideration is, of course, speed. That many different implementations can vary greatly with how efficient they are. But how efficient exactly is it worth the trouble of switching over? And how involved is it to switch from one solver to another? Well, in this video, I'll show you an example of Miller-tucker-zemlin formulation for Traveling Salesman Problem, how some of the most common and most popular solvers accessible in JuMP perform. If you want to first learn more about Miller-tucker-zemlin formulation, so solving Traveling Salesman Problem using mixed integer programming, please check out my other video. So what solvers can I use with JuMP? JuMP is pretty broad. You can express many different kinds of problems, optimization problems to be solved with it, but solvers, which JuMP allows you to access, are not so versatile. Usually they are much more specialized. And one way they're specialized in is that there's a subset of type optimization problems like linear programming or mixed integer programming or quadratic programming, which they even allow to solve. And in choosing the solver for my benchmark, I used JuMP dev, a table of solvers supported by JuMP. So this is a list of packages which implement JuMP interface, and helpfully it lists the types of problems you can solve with each of them, with MI standing for mixed integer programming, which is what I want as Miller-tucker-zemlin is a mixed integer programming problem. What else can we learn from this table? So first of all, even though it's a Julia package and ultimately all of those are Julia packages too, but most of them are wrappers around native binaries, like for instance GLPK solver or Cplex. They are not written in Julia, just the wrapper is. In some of those, it is the case that there's a pure Julia solver as well. Ultimately, for this benchmark, I picked just 4 solvers from the impressive long list of different ones I could use. After applying the first filter of those that can even handle mixed integer programming, I filtered to those that were somewhat more mainstream and also, frankly, easy to install. And what I ended up was GLPK, which is a GNU linear programming toolkit. It's written in C, and it's a very well-known established solver. It's fully open source. EAGo, which is advanced global optimization framework. It's not really specialized in the type of problems I'm solving here, so it's not expected to perform as well, but I was curious how it's going to perform anyway. Plus it was very easy to set up, which is also which makes it attractive as software. HIGHS, which advertised itself as a high-performance parallel linear programming solver, so there's a high hope that this solver would perform well in a benchmark, and indeed I would expect it to perform the best out of the open source ones. And of course Cplex, which is known to be very stable and high performing, but it is closed source commercial solver for which I use Community Edition. A link to this Jupyter notebook you can find in the description of this video if you're curious about some more details. I'm not going to go in depth about the Miller-tucker-zemlin. If you're curious about that, I invite you to watch my other video on the same topic. Or you can go through the code. It's pretty short, pretty concise. I also link in my other video to a blog post which does an amazing job at explaining what each constraint is 4 in Miller-tucker-zemlin. I encourage you to read this blog post. Alright, but back to the benchmark itself. First, we need to set up different solvers. And this is where we clearly see that it is indeed easy, at least technically, to switch from one solver to another. I made a small helper method prep model, which allows me to create a optimization problem for TSP with many different, the different size of the problem, different amount of deliveries that need to be optimized for, and a second parameter being the solver. And you can immediately see the abstraction provided by JuMP shining through, because indeed you can put a different solver in here, GLPK optimizer, EAGo, HIGHS, Cplex, and you almost don't need to do anything special. Almost, because there are always some small differences, because those optimizers, they still have some of their specific parameters. And in case of Cplex, like all proprietary software, they of course have to do things their own way. The way you disable logging output is different than for all the other solvers. So if you don't want to bias your benchmark by unnecessary standard output, you have to pass it. Other than that, I'm using default settings. For the benchmark, I'm using two macros. Add time, which is, as far as I can tell, a very common way in Juliet to time single execution of a function. And the second one, imported from benchmarks. It's a very nice package over here, benchmark tools. It is add benchmark, and it allows to execute given function multiple times. It provides quite some nice facilities, such as a fixture function. So I pass my prep model with GLPK and problem of size 10, and this will be executed each time before the beginning of a new sample. Benchmark uses the notion of evaluations and samples, evaluation being consecutive evaluation on the same setup. So I get one random piece of data and then run, in this case, 3 times the same function on the same data. Samples is the times that I execute the fixture function, the setup, meaning how many different data sets on input I'm going to have. Benchmark is actually meant for CIs, and you can tell by the fact that it generates plots that can be displayed in command line. It's basically ASCII art, very handy for Jenkins, GitHub Actions, Travis, or GitLab CI. And what you learn from it is 2 things: the execution time with some statistics, most pertinent median, and also the memory usage. The memory usage for TSP, and the same as computational complexity actually, grows really, really fast. It's a classic traveling salesman problem. It's also why performance is so crucial in here, and we have to very carefully pick the size of the problem. Sadly, for this formulation, which is quite naive, already problems of size 20 sometimes, at least with open source solvers, don't converge to a solution. This is quite disappointing, but I bet that if I maybe formulated it more cleverly, or just replace MTZ with some more efficient formulation, I could reach higher problem sizes. But for now, I cannot really perform the benchmarks reliably for anything higher than 20. And in fact, I picked 10 because this is the most stable. Of course, the problem will grow really fast, like exponentially. So even though we have a degree of magnitude of dozens of milliseconds for 10, for 20, it will be already 10 times as much, and for 30, 10 times more as before. Okay, but now let's have a look at the actual results. For GLPK, the GNU, the well-established, we have 22 milliseconds. For EAGo, general purpose global optimization one, not so well suited for this class of problem, we have 204, so 10 times as slow, and also 10 times as much memory, interestingly enough, for the same problem. HIGS, which is a high performance open source solver, we have 100 milliseconds and 93 kilobytes, so that's it's 5 times as slow as GLPK. And for Cplex we have 7 milliseconds, which is the fastest of them all, which is also sort of expected. I'm using Cplex Community Edition, and I couldn't go higher than problem size of 30 because it doesn't allow you to use Community Edition for bigger problems. But for open source ones, I couldn't really go higher than 30 anyway, because frequently they just wouldn't converge. Well, so at least for Miller-tucker-zemlin and with default parameters, it seems that Cplex kicks asses of all the other solvers I managed to set up for this problem, and sadly HIGS didn't perform as well. It turns out it is GLPK that's the fastest open source solver I can use with JuMP for mixed integer programming. But well, I'm sure that there's much more performance that can be eked out of this problem, either by formulating it more cleverly or maybe by playing more to strengths of given optimizers. I'll have to dig more into that. Thank you for listening.